friends, welcome back to my YouTube channel Reasons and Logics. Here I am back with a new video on electric charges and fields, and the topics which I would be covering today are electric field, that is its definition, SI units, physical meaning, electric field intensity, all those things we would be covering in electric field. Number 2, electric field due to a point charge, then electric field due to system of charges, then electric field due to continuous charge distribution, finally we'll be doing electric field lines plus their properties. Okay, so let's start with the very first topic of today's lecture, that is the concept of electric field. So electric field is just a space around the charge in which an electrostatic force of attraction or repulsion due to a charge can be experienced by any other charge. So this is the definition of an electric field. Now, to understand the meaning of electric field physically, we introduce a term known as a source charge and test charge. So source charge is the one which generates an electric field, and test charge is the one which experiences the force due to source charge. So we just introduced the concept of source charge and test charge. Let us do them in a more detail. So firstly, source charge. So this is the charge, as I told you, which generates the electric field. Fine. Now, the direction of electric field lines is outwards if source charge is positive and direction of electric field lines is inwards if source charge is negative. So if this is our charge, that is plus Q, so this will be the direction of electric field lines. We'll do it in a detail afterwards, but firstly you should just know that direction of electric field lines will be outwards if the source charge is positive, and if it is negative, then this will be the direction of electric field lines. Fine. Now, Q naught is the test charge. Let Q naught be the test charge. This charge is very small and the electric field which is generated by Q naught is vanishingly small, and this test charge cannot change the position of this source charge, or we say that this source charge does not experience any kind of force due to the presence of this test charge. So this test charge should be chosen in such a way that it is small enough that it does not affect our source charge Q. Fine? Okay. So now we will understand what do we mean by electric field and why do we need an electric field. So basically, suppose that this is the region up to which the electric field due to this charge is spread. And suppose our test charge is placed somewhat here. So at this point, this test charge will not experience any kind of force due to this source charge. That means this test charge will experience the force due to the source charge if and only if it is placed in the region up to which electric field is generated by this source charge. Fine. So basically electric field is the measure of the strength of force experienced by test charge. Fine. So this is what physically we mean by an electric field. Okay. So now let us define electric field intensity. So electric field intensity at a point is defined as force, that is nothing but your electrostatic force per unit test charge acting on vanishingly small positive test charge placed at that point. Fine. So this is what is the definition of electric field intensity. Writing it in a mathematical form, since force is a vector quantity, so obviously our electric field is going to be the vector quantity only. So this is given by, suppose F is the force acting on vanishingly small positive test charge, and since it says that force per unit test charge, so this is our case. Fine. Since we say that test charge Q naught has to be vanishingly small, that means it is almost equal to 0, so we can write it in this way. Limit Q naught approaches to 0. Here we have a force upon Q naught. Fine. But when I was explaining about electric charge, I told you that electric charge is quantized and it has the value having plus minus of Ne. So from this quantization condition, the smallest possible value of the test charge is E, that is 1.6 into 10 raised to power minus 19 coulomb. Fine. So this test charge cannot be 0, but here we are saying that it is just approaching to 0, and the smallest possible value for electric charge is 1.6 into 10 raised to power minus 19. Now suppose that our charge Q naught is positive. Fine. But here we are taking the limit of Q naught approaching to 0. that means our Q naught is somewhat greater than 0, but we are taking it as approaching to 0. Fine. So that means since electric field is inversely proportional to Q naught and this Q naught is greater than 0 but we are taking it as 0, that means measured value of electric less than the actual value. Fine. Similarly, if Q naught is negative, that means Q naught is smaller than 0. So, measured value of electric field will be greater than the actual value. Fine. Now, why do we say that no electric field is generated by the test charge? It is just the electric field of source charge, and test charge just experiences the force due to the source charge. Let us prove that the electric field in this case will not be generated by the test charge. The electric field intensity is given by upon Q naught, where this F is the force due to a source charge on a test charge. Fine. So from Coulomb's formula we have K Q naught upon R square. Fine. Into R cap. So this is our force. Putting this value here, we get what will be our electric field? It would be Q naught upon R square into R cap divided by Q naught. So this Q naught will get cancelled, and whenever we'll talk about the electric field, we'll say it is always generated by the source charge, because in this formula we don't have the test charge. That means test charge has not contributed in this generated electric field. Fine. Now, after this, let us find out what will be the SI unit of electric field. So from here we can very easily say that it has to be Newton per Coulomb. Fine. So with this we are done with electric field intensity, source charge and test charge, and we are all set to move further. So next we are going to do electric field due to a point charge. So suppose we have to calculate electric field intensity due to a point charge Q, and let this position be O. Fine. And we have to find electric field intensity at a point, say P. Fine, which is placed at a distance R0 from our source charge. So while finding electric field intensity, our first task always is to suppose a test charge, a unit positive test charge at the point of observation. So here we have a test charge, say Q0. We have supposed this test charge to be here. Okay. So now let us first write down the formula for Coulomb's force. So Coulomb's force in this case will be, so this is 1 upon 4 pi epsilon naught Q. The test charge is Q0 and distance is R0 square, and let the unit vector from Q to Q naught be R naught cap. Fine. So this is the force exerted by the source charge on the test charge. Next, we know that electric field is nothing but F upon the test charge. So our electric field intensity becomes one upon 4 pi epsilon naught Q into Q naught upon R naught square upon Q naught into R naught cap. So this is nothing but 1 upon 4 pi epsilon naught Q upon R naught square into R naught cap. So this is the formula for an electric field due to a point charge. Okay. Now, next we are going to do electric field due to system of point charges. So, like we did for the case of superposition principle, we'll first derive the formula due to two charges and then we'll extend it for n number of charges. Fine. Suppose here we have charge Q1, here we have charge Q2, and here we at point P we have placed a charge Q0. Fine. So we have to find electric field exerted at Q0 due to Q1 and then due to Q2 at Q0, and then we'll find resultant of the two by adding them following the laws of vector addition. Fine. Now we know that F1 will be equal to 1 upon 4 pi epsilon naught Q1 into Q0 upon R1 P square into R1 P cap. Fine. So this is just a notation, but you should know that what do we mean by this R1P. So this R1P vector is the position vector pointing from Q1 to Q0. Fine. That means in this direction. Okay. So now following the triangle law of addition, from this we get R1 vector plus R1P vector is equal to R vector. So R1P vector is nothing but R vector minus R1 vector. And we know that R1P cap will be equal to R vector minus R1 vector upon magnitude of R vector minus R1 vector. So very clearly our force becomes F1 is equal to 1 upon 4 pi epsilon naught Q1 Q0 upon R vector minus R1 vector magnitude square into, putting the value of R1 P cap from here, we get R vector minus R1 vector upon magnitude of R vector minus R1 vector. So we get F1 as 1 upon 4 pi epsilon naught Q1 Q0 upon R vector minus R1 vector whole cube into R vector minus R1 vector in the vector form. So very easily electric field becomes 1 upon 4 pi epsilon naught Q1 upon R vector minus R1 vector whole cube into R vector minus R1 vector, because we have just divided it by the test charge. So this is the electric field generated by Q1 at point P. Okay. So similarly, following this rule again, we'll get E2 as 1 upon 4 pi epsilon naught Q2 upon R vector minus R2 vector magnitude whole cube into R vector minus R2 vector. Okay. So now let us write if we have n number of charges. So we have got electric field E1 as 1 upon 4 pi epsilon naught Q1 upon R vector minus R1 vector whole cube into R vector minus R1 vector. And this is nothing but 1 upon 4 pi epsilon naught Q1 upon R1P whole square into R1P cap. Fine. So in the unit vector notation, this is the case, and if we have to represent it in a vector way, then this is the correct representation. Similarly, E2 will be equal to 1 upon 4 pi epsilon naught Q2 upon R vector minus R2 vector whole cube into R vector minus R2 vector, that is equal to 1 upon 4 pi epsilon naught Q2 upon R2P square into R2P cap. Following the same rules, electric field due to charge Qn at point P will be equal to En 1 upon 4 pi epsilon naught Qn upon R vector minus Rn vector whole cube into R vector minus Rn vector, that is equal to 1 upon 4 pi epsilon naught Qn upon Rnp square into Rnp cap. Fine. Now, the total electric field due to n number of charges will be equal to E1 plus E2 up to so on to En. So we just have to add it and write it here. So I'll write it in the form of summation. So here we have 1 upon 4 pi epsilon naught summation over I is equal to 1 to n. That means here we have Qi upon R I P square into RIP cap. So this is the total electric field due to system of point charges. That is when we have, say, n number of charges present in the system. Okay. Next we are going to study about continuous charge distribution. Like how our force and electric field will change if instead of discrete charges we have continuous charge distribution. Now, when we were doing quantization of charge, I told you that the values which a charge can take are just integral multiple of E, that is the charge on electron. But when we are talking on a larger scale, it becomes very difficult to talk about a single electron. Fine. Suppose we have this conductor. So it becomes very difficult to specify that how many electrons are present here, how many electrons are present at specific location. So instead of talking about specific locations, we talk about specific regions. Fine. That means in this particular region, what is the concentration of electrons? So instead of counting the electrons in a discrete way, we talk about their continuous distribution. Fine. Now see how can we do that. So for that we define a quantity known as surface charge density. What do we mean by surface charge density? So surface charge density is represented by sigma and it is defined as delta Q upon delta S, where delta S is the small area that we have chosen for our measurement. Suppose this is delta S and delta Q is the small charge contained in this area. So what we do, we choose different areas like this and we find surface charge density of each region, and when we add it at the end we get the continuous and complete surface charge density of this conductor. Fine. Similarly, if we have charge distributed on a line, then we define line charge density, that is given by lambda, and that is equal to delta Q upon delta L. This is the length which we have chosen, and this is the charge contained in this length segment. Fine. And lambda is the line charge density, or we call it as linear charge density. Next is the volume charge density. This is used for the cases if we talk about a cube or a cuboid. Then we talk about volume charge density, and it is represented as rho, given as delta Q upon delta V, where delta V is the volume in which delta Q charge is placed. Okay. So now let us see how our force will change if instead of choosing Q we choose surface charge density. See. Now, to understand the concept of continuous charge distribution, here at point P, instead of assuming a point charge, we have assumed a complete cube or a complete volume region where the charge is present. Now suppose that initially we choose a small region, that is delta V, from this complete region in which delta Q charge is present. Fine. So firstly we find a small force due to this small charge exerted on this test charge, and let that small force be represented by dF. Following the Coulomb's law, this becomes 1 upon 4 pi epsilon naught delta Q into Q naught upon R10 square into R10 cap. Fine. Now, we know that volume charge density rho is equal to delta Q upon delta V. From this equation, we can get delta Q is equal to rho delta V. Putting this value of delta Q from this equation into this equation, we get dF as 1 upon 4 pi epsilon naught into Q naught into rho delta V upon R10 square into R10 cap. Fine. Now, this is the force due to the small charge delta Q present in the region delta V. So, now what we'll do, we'll choose different delta V's for this entire region, and by using superposition principle, we'll find the total force exerted by this charged region on test charge Q naught. So now let the total force be represented by F, that F will be equal to Q naught upon 4 pi epsilon naught summation over all delta V's into rho delta V upon R10 square into R10 cap. Fine. Now, this is the case if we choose a delta V such that it has a finite width. See, I'll explain. If this is the region, suppose that this is a 3D region just for the sake of understanding, and suppose this is the width of delta V that we are choosing. So then this formula is fine for this case. Now, what if we start reducing this width? What if we have this kind of case? So this width has started to reduce. So we have started reducing this width, and ultimately as delta V will approach to 0, this will become a continuous region like this. So then instead of using summation, we use integration. So whenever delta V approaches to 0, summation is replaced by integration. Fine. And for that, force becomes Q upon 4 pi epsilon naught over entire delta V, rho delta V upon R10 square into R10 cap. Fine. Okay, so now we have to find electric field. So the formula for force that we have got is Q naught upon 4 pi epsilon naught integration over entire volume region, and here we'll have rho delta V upon R10 square into R10 cap. Now electric field is simply force divided by the test charge, that is 1 upon 4 pi epsilon naught rho delta V upon R10 square into R10 cap. So this is the expression for the electric field due to continuous charge distribution. Now from this formula only we can write the formula for the cases where we use linear line segment or the area segment. Fine. That is, if instead of having, like here we had a cuboid or a cube, so in case of line segment we'll have some this kind of region, that is some linear region, and for the area segment we'll have say square or triangle or rectangle present there. So for line segment this electric field becomes 1 upon 4 pi epsilon naught lambda into delta L upon R10 square into R10 cap, because here delta Q is equal to lambda into delta L. Fine. And for the area segment electric field will become 1 upon 4 pi epsilon naught sigma delta A upon R10 square into R10 cap, where delta A is the area segment chosen, and in this case delta Q is equal to sigma delta A. So these are the expressions for the electric field due to continuous volume charge distribution, linear charge distribution and surface charge distribution. Okay. So our next topic is the electric field lines. So let us first define electric field lines. An electric field line basically is a path, either a straight path or curved path in electric field such that tangent to it at any point gives direction of electric field intensity at that point. Fine. Suppose we have an electric field line, say from A to B. Fine. So if we draw a tangent at this point, say this, So at this point, this is the direction of electric field. At this point, this is the direction of electric field. So basically, this is a path straight or curved in an electric field such that tangent to it at any point gives the direction of electric field. Now, let us draw the directions of electric field for different cases. Suppose we have a single positive charge. As already explained, direction of electric field lines will be outward. Fine. So this is the sort of electric field lines we get in case of a positive charge. For the negative charge, this is the kind of electric field lines observed. Okay. Suppose we have a positive charge and a negative charge. So basically, they'll show some sort of a direction, and we know that from positive charge direction is outward and for negative charge direction is inward. So ultimately we get the direction from positive to negative if we have two charges present. So this is the kind of electric field lines observed in this case. And from here it will be simply like this. And this, and from here this will be the case. Okay. Next, if we have both positive charges present, so they will repel each other, and the kind of electric field lines observed will be like this. And so on. This is how we can represent electric field lines for the different cases. Okay, so now let's proceed towards our last topic for the lecture, that is properties of electric field lines. Okay, so the very first property is that electric field lines are continuous. Fine. So these are continuous curves and not discontinuous. So if we have a positive charge and a negative charge here, so they'll start from a positive charge and end up here. But they will not form a closed loop like this, like from negative to positive, positive to negative. So electric field lines are no doubt continuous, but they do not form closed loops. Fine. They are not discontinuous, but they do not form closed loops. They are just continuous. That is, they start from one point and end at the other point. Suppose we have a single positive charge. So in this case, electric field lines start from the positive charge and end up at infinity. Similarly, for negative charge, they start from infinity and end up at negative charge. Fine. So this was the first property of electric field lines. The second property is no two electric field lines intersect each other. Why is this so? Suppose that this is how our electric field lines are intersecting. Fine. So at this point we can have two directions of the tangent, one like this and one like this. This. Yeah. So one like this and one like this. That means at single point we are having two directions of electric field. That is just not possible, and that's why we say that no two electric field lines can intersect each other. Next important property is that electric field lines are always normal to the conductor, normal to the surface of the conductor. So if this is the conductor, this board is the conductor, and say it is positively charged, so this will be the direction of electric field lines, from this to outward, or from backside from this to backward. So this is always normal to the surface of conductor. It is not like this will be the direction of electric field lines if this is the surface. So that is what we mean by electric field lines are always normal to the surface of conductor. Okay, so these were few properties of electric field lines. So friends, this was all about today's lecture. I'll see you all soon in my next video. Till then, take care. Bye-bye. If you like this video, do like it, share it, and don't forget to subscribe my YouTube channel. You can also follow me on Instagram. My Instagram ID is mentioned on the screens and link will be mentioned in the description box. Thank you.